In this video, we're going to discuss techniques for finding the derivative faster than using the limit definition. And before we get into that, let's talk about different notations, different ways that we can write a derivative. So if you're given a function, y equals f of x, you can note or denote that the derivative is shown in either of these four manners. So let's talk about what each of those mean. This first one here reads as f prime of x. That stands for the derivative. That's probably the most popular notation. Looking at the second one, dy over dx. That one would read as the derivative of y with respect to the variable in the denominator, so with respect to x. So the derivative of y with respect to x. The third notation here, that is the derivative with respect to x of the function f of x. And the fourth notation is just a different way of writing that ddx. So noticing the difference here, in purple I have this circle, dy over dx. That is the derivative of y with respect to x. Whereas here we have the derivative with respect to x of the function. And the function is y, so it's kind of like sliding that right there into the numerator. So thinking about this, we really just want to make sure we understand these notations. The first two, f prime of x and dy over dx, those are the two that we will use most commonly. So now that we know the notation, let's look at some basic rules. The first rule here says, or is the constant rule. And so if we have a function that is a constant, so f of x equals a number, k is any real number, then the derivative f prime of x, or the derivative with respect to x of k, is 0. So essentially we are just remembering here the derivative of a constant function is going to equal 0. Now remember, derivative represents slope. And if we consider the graph of a constant function, it's a horizontal line. What is the slope of a horizontal line? The slope of a horizontal line, m equals 0. So this makes sense that the derivative of any constant function will always equal 0. The second rule we have here is the power rule. So this deals with any function which is a variable raised to a power. And by that, we mean x to some number. So x squared, x cubed, x to any power. The derivative f prime of x is equal to the derivative with respect to x of that function, x to the nth power, or rather n times x to the n minus 1. So whatever we have in the exponent, that value comes in front, and then we subtract 1 from that exponent value and leave it up there. Or the derivative of f of x equals x to the n is found by multiplying the exponent n, so that you multiply it in the front, and you decrease that exponent value by 1. So this brings us to a third rule. A constant times some function. And for now, we're going to assume that our functions are always some x to the nth power. So if you have k representing a real number, that just means k is any number, and this g prime of x exists, so that means this is a derivative that we can find, then if we have the derivative of f of x being equal to k times some function, and potentially that function is a power function x to the n, so k times x to the n, essentially f prime of x, or the derivative with respect to x of f of x, which is k, times this g of x function, that's going to equal 2k times g prime of x. So essentially, when the function has a constant in front, just take the derivative of the function and leave the constant in front. Or rather, the derivative of a constant times a function is the constant times the derivative of the function. We have one more rule that we're going to add here. And this is the sum or difference rule. And essentially, this just says that if f of x equals a function plus or minus another function, and we can find the derivative u prime of x and v prime of x of each of those functions that we're summing together, then the derivative f prime of x equals the derivative with respect to x of u plus or minus v of x, which will equal u prime of x plus or minus v prime of x. And all this is saying is that we are just going to take the derivative of each of those terms individually. So the derivative of a sum or difference of functions is the sum or difference of the derivatives. So if we have a polynomial, like something quadratic x squared plus 5x plus 10, we would just take the derivative of each of the terms. So let's look at a couple of examples where we apply all of these rules together. For the first example here, we're going to find the derivative of this function. And what we have here is y equals x to the fifth. So when we go to calculate the derivative, we're going to say the derivative with respect to x of y. And that means we're taking the derivative with respect to x of x to the fifth. Now here, x to the fifth, this is a variable raised to a constant power, so we can apply the power rule. And what the power rule says is that we take that power, we pull it out in front as a multiple, so it's going to become 5x, and then we reduce that power by 1. So 5x to the 5 minus 1, or rather the derivative of y with respect to x equals 5x to the fourth. All right, let's look at another example. In this example, we're going to find the derivative of the function f of x equals 3x to the negative 5 plus 2. Now you see we have two terms here. So because of my sum and difference rule, essentially I'm just going to take the derivative of each of these terms individually. So the derivative f prime of x, and it's important that you write this, you don't just start off writing equals and then change it, because that would imply that the function is now equal to that. You have to write f prime of x represent, now we're finding the derivative. So f prime of x will be the derivative with respect to x of 3x to the negative 5 plus 2. Or rather, the derivative with respect to x of 3x to the negative fifth power plus the derivative with respect to x of 2. So for this first term, I used the sum and difference rule to split it up, but for the first term, I'm going to leave that constant multiple 3 in front. That's a constant multiple, so I have 3. And then dealing with x to the negative fifth, that's going to be negative 5x to the negative 5 minus 1. And looking at the last term here, that's the derivative with respect to x of 2. 2 is a constant. So by the rule, the derivative with respect to x of 2 is going to equal 0. So let's clean this up and simplify. 3 times negative 5 gives me negative 15x to the negative 6. Again, that's equal to f prime of x. Your answer needs to say f prime of x or dy dx. Let's just do a couple more examples while we're in this video to really emphasize these rules. For this example, we're going to find the derivative of q of r. Q of r is equal to 5r to the fourth minus r cubed plus r squared over 12 plus r plus 100. So I have 1, 2, 3, 4, 5 terms here. This is the sum or difference of all these terms. Essentially, I'm just going to take the derivative of each term. So my derivative, q prime of r, is going to be the derivative of each of those 5 terms. So I'm going to write the derivative, and instead of with respect to x, in this situation, since my independent variables are, it's the derivative with respect to r. My first term is 5r to the 4th. I have minus the derivative with respect to r of r cubed plus the derivative with respect to r of r squared over 12 plus the derivative with respect to r of r plus my 5th term, the derivative with respect to r of 100. All right, so let's consider each term individually. Q prime of r. This first term here, 5r to the 4th, the 5 is going to remain in the front, and then the 4 exponent comes down. That becomes 4r to the 4 minus 1. I then have a minus. My next term, r cubed, that 3 comes in front, so that's 3r to the 3 minus 1. My next term, derivative with respect to r of r squared over 12, keep in mind that's the same as writing 1/12 r squared. So I'm going to say plus 1/12, and then taking the derivative of r squared, that's 2r to the 2 minus 1. The derivative with respect to r of r, that power on the r is 1. There's a little invisible 1 there, so this becomes 1r to the 1 minus 1. And then for our last term, the derivative of a constant, 100 is a constant, is 0. So you don't really need to write that. I'm just writing that here for emphasis. All right, so let's clean this up. Q prime of r equals 20r cubed minus 3r squared. 2 over 12, that's going to be plus 1/6. r, 2 minus 1 is to the 1st power, which doesn't need to be written, plus 1 r to the 0th power. And anything to the 0th power is equal to 1. So that's essentially saying 1 times 1. And of course, we do not have to write that plus 0. So my final answer, Q prime of r, is 20r cubed minus 3r squared plus 1/6 r. And that's completely acceptable as our final answer. However, you may look at this and recognize that part of it could be factored. So we could also say Q prime of r is equal to, I'll factor out a GCF of r. So that is 20r squared minus 3r plus 1/6. That is not necessary, but that is just another step we could take, because as we look at simplifying, we do always want to try and factor if we can. For our third example, actually I think this is the 4th, we have s equals negative 2t squared minus 5 over t cubed plus the square root of t plus 8t. So again, we can take the derivative of each of these terms, treating this like a polynomial. However, it doesn't look exactly like a polynomial, and these 2 terms in the center are what looks a little bit problematic to us. So before I do anything, I'm going to kind of use algebra here to rearrange my problem. So that's negative 2t squared. I'm going to write that t cubed in the denominator. I'm going to move that up, and that is negative 5 or minus 5t to the negative 3. I'm going to write this root t, that's a square root, or rather t to the 1/2 power, and then plus 8t. So here, now when I go to take my derivative, I'm going to say the derivative with respect to t of s. And that's going to equal the derivative with respect to t of negative 2t squared minus the derivative with respect to t of 5t to the negative 3 plus the derivative with respect to t of t to the 1/2 and plus the derivative with respect to t of 8t. So that gives us the derivative of s with respect to t. My first term here, negative 2, I've got 2t to the first. 2 minus 1 gives us the first power. My second term, minus, leave my coefficient 5 in front, and that is negative 3t to the negative 3 minus 1 is negative 4. My third term, there's no coefficient, so I'm just going to go ahead and write my plus. My power 1/2 comes in front, so I've got 1/2 t, and 1/2 minus 1 is negative 1/2. So I have a negative 1/2 power here. And then for my last term, 8t, the 8 comes in front, and I have t to the first power, so that's 1t. T to the first is 1 minus 1, or essentially 0. So simplifying this, if I were to write my final answer, the derivative of s with respect to t is negative 4t plus 15t to the negative 4th plus 1/2 t to the negative 1/2. And then this last one, t to the 0th, that just goes away and we have plus 8. So for our very last step, I always encourage you to return the problem in the same format that it was given to you. So ds dt equals negative 4t. Since we didn't have a negative exponent that was written rationally, I'm going to rewrite this. That's going to be 15 over t to the 4th. And then I'm going to get rid of this rational exponent, and negative puts it in the bottom. The 1/2 means it's going to be a square root as the power. So this is 1 over 2 square root of t. And then we have plus 8. Either are fine, but when you are dealing with the computer, oftentimes the computer wants you to return the answer again in the same format that it was provided. So since this t was in the denominator, we didn't have a negative exponent, we didn't have a rational exponent, we wanted to clean those up. All right, let's just look at one more problem where we can use algebra first to simplify. So again, we're asked to find the derivative. We have y equals this quantity, square root of x plus 8x squared, all divided by 3x. Now, this does not look like a polynomial, but if we use a few of our algebra skills, since I have two terms divided by 1, I can write each of those terms, which occur in the numerator, square root of x over 3x plus 8x squared over 3x. Now, each of these can be simplified. keeping in mind this is the same as y equals x to the 1/2 over 3x. And looking at this, since I have x squared divided by x, essentially that is just 8/3 with an x in the numerator, or you can write it in the back. And then thinking about this, we have x to the 1/2 over x to the first. When you're dividing like bases, you can subtract the powers. So this is the same as saying 1/3, that 3 in the denominator, and we have x to the 1/2 minus 1. And x to the 1/2 minus 1 is negative 1/2 plus 8/3 x. So I haven't done any calculus at all yet. I've just rearranged the way this looked. I used my algebra skills to make it look like a polynomial. At this point, we'll use our power rule. So the derivative of y with respect to x, that is 1/3. I then have negative 1/2 x to the negative 1/2 minus 1. And for my other term, I have 8/3. And then I have 1x to the 1 minus 1. So I used my power rule on each of these x variables. And the way this will simplify here, dy dx equals negative 1/6. Negative 1/2 minus 1 is x to the negative 3/2. Then I have plus 8. Because 1 minus 1 is 0, and x to the 0 is equal to 1. So essentially we have times 1 there. So this is fine as my final answer. So I just did, I think, 6 examples using the power rule and the sum and difference rule and the constant multiple and the derivative of a constant. And I hope that helps you understand this process a little bit better. The best way to get better at something is to practice. If you do have any questions, please feel free to email me, check in, let me know what you are thinking. Have a great day.